So convolution is an extremely important concept. Many people associate convolution mainly with convolutional neural networks. Sometimes people think CNNs are no longer important because transformers exist. But that is not true. There are two main reasons. First, convolutional neural networks are still widely used because they are lightweight compared to large transformer networks. Second, convolution goes far beyond neural networks. It's a fundamental mathematical operation used to understand how two signals interact with each other. When we apply convolution, we are essentially mixing two signals in a structured way. What we want to measure is not just similarity, but how similar two signals are when one is shifted across the other. So convolution gives us a precise way to measure correlation between signals across positions. Because of this, having a strong understanding of discrete convolution is extremely important. So now why are we discussing discrete convolution? Because almost all signals in computing are discrete. For example, an image is made of pixels. Each pixel has RGB values. Each value is a specific number. So the signal does not change continuously. Instead, it changes step by step. Therefore, an image can be viewed as a 2D discrete signal. In fact, computation itself is discrete. Computers process indexed values, not continuous functions. So our goal is to understand how convolution works for discrete functions. So suppose we have two signals x and h. Later we may call here this h as the kernel function, but for now both are simply functions. The horizontal axis is usually called time in signal processing, but here it is just an index. So 0, 1, 2 and 3. The only thing that matters is the ordering. Each signal has samples like x0, x1, x2 and x3. So our goal is to compute how similar these two signals are. But we do not compute one global similarity or just one value. Instead, we take small overlapping partitions like this. So before moving into this, suppose this is the reference line or the 0, and we define this function as x of n. So n is the indexing value in this function and k is the indexing value in this function or the signal. So first we measure the similarity between these two overlapping portions, and next we expand this overlapping partition like this and this. So instead, like, we take small overlapping portions, we expand it and measure similarity step by step. So we compare chunks of signals at different positions. The question becomes, how similar are these signals as one moves across the other? So this is not just the similarity. We are not measuring the dot product between these two signals directly. Rather, we measure the similarity while shifting one signal across the other. So before moving into that, so again, this is the system we are considering, and I want to flip this signal x. How are we going to flip the signal? We take x of -1 like this. So this is the previous signal and now we have flipped it. So essentially this is the mirror image. If there was a mirror along this y-axis or the c at the 0. So this reverses the complete signal. Next, we place both signals on the same axis. So this reversed signal and the original signal. So how are we going to do this? Like this. And At each position, we multiply overlapping values. So how is this going to work? So we shift this function x step by step, and then we multiply overlapping values and sum them. So it's like this. So we shift it by 1, and this is the overlapping part, and we multiply them. So here there's no need to add anything because it is only one value that is being overlapped. In the next step, we shift another step. So what are we going? Actually, I have done a small mistake here. This must be k. And so now we have two overlapping parts. So how are we going to measure the similarity? We multiply each of them and we add them up. So we do this again. And again, now we have three overlapping positions. We multiply them up and add. So this is simply a dot product between overlapping parts. So each shift gives us different similarity score, and these scores form the output signal or the result of the convolution operation. So we can write this convolution using the summation notation. Here, k runs over the indices where the signal overlap. N represents the shift. And in our example, signals have limited support, so they are not extended from minus infinity to plus infinity. And this means they exist only over a finite range. They are not defined from minus infinity to plus infinity. So we only sum over indices where values are non-zero. As a result, we have a finite support signal as the result also. The resulting signal is also going to be a finite support signal. If needed, we can imagine padding the rest with zeros. Then the general formula becomes, so all the other values which are non-zero, so non-zero values, we have these non-zero values, all the rest of the values we are going to consider them as zero. So the general equation becomes this. So we sum from minus infinity to plus infinity, but practically only a few terms matter because rest of them are just zeros. So each output value y0, y1, y2, we can define each one as a linear equation. So this is our key equation, and you may have seen this especially in signal processing, but I hope now you have an idea on what we are measuring. We are measuring the similarity between two signals, but the important fact we must understand is it is not the raw similarity value we are measuring. We are taking one signal, flipping it up and moving across the other signal, and in each step we measure the similarity. Actually, the way we are measuring the similarity, we can call this operation as a dot product. So each of the resulting values, we can write them as linear combinations of the two signals, or simply dot products, and we have a set of equations for our original system we discussed earlier. So since every output is a linear combination of inputs or the two signals, we can rewrite the convolution. So actually here, as I mentioned earlier, we take the signal h as the kernel and signal x as the input. So kernel is something that is happening inside the machine, and input is what we give to the machine, and y is the output of the machine. So h kernel actually kernel defines a machine. That's what in terms of signal processing, that is the best way to think of this kernel function or the kernel signal. Actually, in other words, we can think of this kernel function as a response signal. rather than just like simply calling it a function. So either way, we have this set of linear equations, and we can, like, if you are familiar with linear algebra, a set of linear equations can be written using a matrix. So how are we going to do that? We define this equation. So now, so we can think this is the input, this is the machine, and this is the output. So interesting. But so this is this matrix. So we call this capital H, and this matrix is constructed from the kernel values, as you can see here. So this matrix has a very special structure. Only elements around the diagonal are non-zero. Why? Because convolution introduces locality. Each output element depends mainly on nearby input elements. The main diagonal corresponds to each element interacting with itself. And slightly off diagonal terms correspond to looking slightly left and right. So far elements are zero because they do not interact. This matrix is called a Toeplitz matrix. So convolution naturally connects to multi-layer perceptrons. How? So rather than writing this whole matrix equation, I will write this as this. So y equals h times x. X is the input, h is the kernel matrix, and y is the output. So this is extremely similar to what we discussed in multi-layer perceptrons. So if we replace this function h, this function or the kernel matrix h with w, then this is essentially a multi-layer perceptron without bias. So convolution naturally connects to multi-layer perceptrons. So you can think of convolution as a special case of an MLP where most weights are zero and weights are shared and interactions are, so all these weights are being shared across the inputs and interactions are local. That's why the diagonal elements or the elements that are close to diagonal are non-zero and rest of them are just zeros. So now we have discussed the essence of 1D convolutions, but the real interesting fact hides behind 2D convolutions. So now let us extend this idea to images. An image is a 2D signal given here by xmn. And also we have a kernel hkl. So we place the kernel on top of the image and begin sliding it. But unlike 1D convolutions, movement now happens in two directions, left to right and top to bottom. So that's why the output must have two indices. So how are we going to do this? It's like this. So we slide this kernel across the image like this. Like this. So we are moving in two directions, from left to right and top to bottom. Each kernel position produces one output value. So in practical applications, the image is given, but the kernel function h is learned. Actually, this is the 2D convolution function, and this is similar to the function we discussed earlier, but now we have two indices. And in convolutional neural networks, actually this signal or the image is fixed. The kernel parameters are optimized during training. They are just learned. the kernel is made up of learned values. So the network learns which patterns are useful. So in theory, convolution includes flipping. But in deep learning implementations, flipping is usually ignored. So what is computed is technically a correlation, not strict convolution. However, since the kernel is learned, flipping or not flipping makes no difference. And now here in this equation we have flipped, but actually in the original implementation of convolutional neural networks we do not flip, and the resulting convolutional kernel, the learned convolutional kernel, we can think of it is flipped rather than it is being flipped by ourselves. So it itself going to be flipped. So therefore we still refer to the operation as convolution. So this is the 2D convolution equation. And as the kernel moves across the image, each position produces a similarity value as we discussed earlier. And this completes the idea of discrete convolution in 2 dimensions. Actually, there's no need to stop here. Like we can extend this to 3 dimensions, 4 dimensions, or suppose we are thinking like there are 3D convolutions where like in 3D graphics we use voxel grids, voxels, not pixels but voxels. So like we recreate our environment using small boxes rather than 2D patches. So as a result we call them voxels. So voxel grids are processed using 3D convolutions. So rather than using 2D kernel, now we have a 3D box, and that is the kernel. So we can extend this to any sort of signal, no matter how many dimensions we have, but still the core theory is valid. So hope you understand what discrete convolution really means, and hope you will be able to apply this understanding or the intuition you gained here in understanding further topics like Fourier transform, fast Fourier transform, and how can we use convolutions inside transformers. All these things are very interesting, extremely interesting topics, and I hope this video will be a great guide when you are exploring those ideas.